Good morning, here we are. It's the physics video lecture, Physics 105, did I write 105A? B. Video lecture 11. Okay, so I brought the pendula in that I had been talking about last time. And let's start the hour off with the demonstration of these pendula here. So they're reasonably identical, and so they have the same period frequency. Demonstrate that way, right? They keep the same beat, and they're reasonably frictionless as well. So that would just be two pendula, but what we can do is couple them with a light spring. So we put the spring here. If we can, there we go, that's one side. And now we have what are called two different modes. This is a pretty light spring. In the ideal case, the spring is massless and has no effect on these. And so now they're swinging the way they did before, same frequency. But the other thing we can do is pull them apart. Okay, we can pull the two pendula apart, and now that we put a little energy in the spring, and it's also gonna have a greater restoring force, and it's gonna have a push out as well, a greater force in both directions, which means that there will be a slightly higher frequency. The spring is weak, so you don't actually see that the frequency is slightly higher, but it is, very slightly, just based on the forces involved. So here's the phenomenon that this thing is designed to demonstrate. We're going to leave one of these masses at rest and pull this one out and let go of them both at the same time. And there we go. Actually, I'll point from this side. So what you're going to see is that the initial displacement is decreasing, and that pendulum now has come to a dead stop. All the motion is on this one that was initially at rest, and now it's going to reverse itself. And now pendulum 2 is about to come to a dead stop. There we go. And pendulum 1 is swinging with its full amplitude again. So in the ideal system, this will go on forever. Okay? And this exchange of energies is referred to as beats. Okay? These two frequencies. So you could say there's a beat frequency. It's much smaller. That's the frequency with which these pendula exchange their energy. Good. So we're going to demonstrate this mathematically now. And the system we're going to use is the one we finished analyzing, or we started analyzing in the last lecture. So let's remind ourselves. Well, first of all, just put this here for your notes. Coupled pendula model that was built here, as a matter of fact. So we have these two pendula in this frame, and we have a spring there. You guys were analyzing this thing, and I said go ahead and put the spring L and L. I said go ahead and put the spring down here. That was just so you could have a mathematically well-defined system, easier to work with. The phenomenon's exactly the same. Coupled pendula and beats. And what we're going to see mathematically, when K is sufficiently weak, you get this beat phenomenon. So now let's look at the system that we're going to analyze. Remember, we said this one is equivalent to our two masses and three springs. So 2 masses, 3 springs. Let's go ahead and list everything we know about this thing. Okay. So over on the left side here we have a spring, got a frictionless mass. We have another spring connecting to the second mass. This is spring constant K, this is K prime, and this one again is K. So we're on the x-axis and we're measuring the small displacements from their equilibrium points. So we found a number of things that we're going to, so first we're going to write down everything that we found. So we had x1 of t is equal to, actually no, let's go, we're going to list all of our results there. So we had the Lagrangian, okay, we get the Euler-Lagrange equations, those are in your notes as well. We found minus omega squared m plus k determinant equals 0, where this matrix M was M, 0, 0, M, and this matrix K, a little too small right there, go underneath. This matrix K was K plus K prime minus K prime minus K prime, K plus K prime. Then we found the frequencies. I'm going to call them omega 1 and omega 2 this time. Omega 1 was equal to root K over M. Omega 2 was equal to root K plus 2K prime divided by M. Those were the frequencies. This one is larger than the first one there. In the limit as that spring becomes weak, of course, the two frequencies are the same. That's the same thing I discussed with the double pendulum right there. Okay, so what are our solutions? This is what we had there. Solutions to the system were x1, x2 was equal to alpha 1, 1, 0 e to the omega 1 t plus alpha 2 1, 1, 1 minus 1 e to the I omega 2 t. That was the general solution to this problem here. What we had found was eigenvalues. Let's continue here first. Are the eigenvalues. Hope you left some room here. Are the eigenvalues and 1, 1, 1 minus 1, the eigenvectors. This one I required as a homework assignment. Leave some room in there. Very easy to get, okay? So I just wanted to make sure. Eigenvectors. Yeah, in terms of that homework assignment that I had mentioned, what you do is you go back into the matrix with first the omega 1 and then solve the matrix equation here. and ditto with the other one. Okay, so definitely these eigenvectors. If anyone has questions about that, I'll demonstrate it here at the board, but I thought it was a pretty basic problem, two-dimensional eigenvectors. So yeah, the solution here, the general solution to this linear differential equation with constant coefficients is a linear combination of the two solutions that we found, okay? So general solution is a linear combination. So what I'm calling alpha here, of the specific solution, what I'm calling alpha 1 and alpha 2 are arbitrary constants. These are the eigenvectors, and these are the functions that we just found. Okay. So we have to convert that into the motion that we just demonstrated here. And that's an interesting problem. So first of all, a couple of notes here. Right now, everything is complex. You know, these vectors are real, but these can be thought of as complex, obviously, and these alphas can be thought of as complex. We want the real part, okay? Real part of the complex solution. Okay. And x1, x2, right? That's the motion of x1, that's the motion of x2. So if you just look at x1, you see it's a combination of the sinusoidal function with frequency omega 1 and omega 2. If you look at x2, it's also a linear combination of those frequencies omega 1 and omega 2. So what we're going to do next is turn this general solution into the description of this actual system here. So yeah, this general solution, the linear combination that we have here, then we have to take the real part of that solution. So we'll write down real parts. And this is the thing we're talking about. I'm going to go ahead and erase all of this. Okay, so we're going to translate that into the following. So this is going to be a real expression. So we're going to have x1 of t. And what do we have here? Generally, this is a cosine plus I times the sine. Okay. For omega 1t, you can say x1 of t is equal to a cos omega 1t plus b sine omega 1t. Okay. And then here we would have also fully general plus c cos omega 2t plus d sine omega 2t. That would be the fully general version of a real part of this top expression here. Okay. And the reason I'm going to cos and sine in that way, I could also express this as cosine omega t plus phi, right, plus a constant. But we know that that's equivalent to A and B with cos omega and sine omega. So if you accept that this is fully general for the top row, x1, then you'll see for x2, we have the same thing. We have A cos omega 1t plus b sine omega 1t. But over here we'll have the minus sign, minus c cos omega 2t minus d sine omega 2t. So that's the fully general expression, and that's a little too complicated for our case, right? But we see where it all came from. Next, we're going to talk about the initial conditions of our system. So the initial condition are going to simplify this quite a bit. And what are the initial conditions? It's like with the pendulum. I held them both at rest, and I released one with an initial position. Okay, so x1, 0, or x1 of t equals 0. Let's put it right there. x1 of t equals 0 is equal to x1, 0. x1 dot of t equals 0 is equal to 0. That means I released it from rest. And x2 of t equals 0 was equal to 0, and x2 dot of t equals 0 was also equal to 0. So just to remind you, we're talking about the two masses of 3 springs. But what I did here, pretty clear, I held x2 at rest, I held x1 right here, and then I released them. So the initial velocities were both 0. One of them had an initial position, okay? And I released them from rest. Good, so now we put the initial conditions in, or we formulated them, and we should be able to see some stuff right away. So the x1 of t equals 0, x1, 0, we have, here I'll make some room up here. Okay, so we have those 4 conditions. We can evaluate them and nail down what everything means. So at t equals 0, x1, 0 is going to be equal to a cos omega t is 0 to 1, b is 0 plus c. Okay, everything else just vanishes. x2, 0, for the, this is this condition right here. The next one, this one right here, I have a 0, and when I plug in, I have a minus c. A minus c, those are trivially 0. So already we have a is equal to c is equal to x1, 0 divided by 2. That simplifies things. Now we have to take a derivative. I'll do that over here. So x1 dot is equal to minus omega 1a sine omega 1t plus omega 1b cos omega 1t minus omega 2c sine omega 2t plus omega 2d cos omega 2t. And then at time equals 0, we're going to get a 0, 0 there, we're going to get omega 1b, get a 0 here, plus omega 2 d. And then we have to do x, so we'll put a box around here. And we have to do x2 dot equals 0. So x2 dot equals minus omega 1a sine omega 1t plus omega 1b sine omega 1 cosine omega 1t cos omega 1t plus omega 2c sine omega 2t minus omega 2d cos omega 2t. And when we evaluate these at 0, we get 0 equals omega 1b x2 omega 1b minus omega 2d. And so this is interesting. So we have these two equations here. Write them out clearly, and what you'll see is if you add the two equations, these cancel, and then you get b is equal to 0. And you subtract them, likewise, you get d is equal to 0. In fact, you add them, you get b is equal to 0, then d is also equal to 0. So that's nice. These two equations imply that b equals d is equal to 0. So now we have a much more manageable system, having evaluated the initial conditions, and I'll write down what we now have. So now x1 of t is equal to, we just had a and c, so x10 over 2 cos omega 1t plus cos omega 2t, and then x2 of t is going to be x10 over 2 cos omega 1t minus cos omega 2t. Minus cos omega 2t. And if you look at your initial conditions, you can see when t is equal to 0, you get both of these 1s, you get x10. And of course, when t is equal to 0, the difference of those vanishes. So we have a solution, but we're not ready to declare victory yet because we don't actually see what's going on in this solution. So let's analyze this further. So what we're going to do now is note that we've got this omega 1 equals root k over m. Omega 2 is equal to root k plus 2k prime over m. So one of these is greater than the other. And there's a nice geometric way to deal with this. And so here's omega 1, here's omega 2. So we can take their average. So let omega equal omega 1 plus omega 2 divided by 2. That's right smack in the middle there, right? There's our omega. On some scale there. And then let alpha equal omega 2 minus omega 1 divided by 2. Okay. And what that means is I can refer to omega 2 is equal to omega plus alpha, and omega 1 is equal to omega minus alpha. Okay. Just by doing this on the number line, obviously if I do the couple algebraic steps, it's going to come out the same way. So we have omega 1 is equal to omega minus alpha, omega 2 is equal to omega plus alpha. And what we're going to do is plug these into here and get a really nice result. So what we now have is x1 of t is equal to x10 divided by 2 cos omega minus alpha t plus cos omega plus alpha t equals x10 over 2. Now we have these addition theorems here, so that's cos omega t cos alpha t plus sine omega t sine alpha t. And here we're going to have same thing, but cos omega t cos alpha t minus sine omega t sine alpha t. So these go away, and we're left with the following. x1 of t is equal to x10 cos alpha t cos omega t. And if you do the same thing for x sub 2, you're just subtracting where you added up here. So you're getting rid of the cosines and retaining the sines. That's the only difference. So I can write x2 of t is equal to x10 sine alpha t sine omega t. So finally we've obtained this result, and I'm going to graph it for you now, make some sense of it. Okay. And here's what I'm going to do. I'm going to write out larger, put a bracket around x10 cosine alpha t. So it's just cosine omega t. And same for x2. Put a bracket around x10 sine alpha t sine omega t. What we're now going to do is graph these two functions stacked like this. So this is a pretty big graph. So there's our t-axis. This is x1, and this is x2. Now the case that we're interested in, that I demonstrated with my pendulum apparatus, was when alpha, so consider alpha much less than omega. Consider alpha much less than omega. So what is that on our number line? Well, actually, everything is really clear right here. So if alpha is much less than omega, it just means that omega 2 and omega 1 are very close to each other. which means that this 2K prime is small, which means that this middle spring is very small. Okay. So that's the case for, so i.e. K prime is much less than K. It's a weaker spring inside there. And what we can do then is see that this is a very slowly changing function. So the bracket is a sort of a slowly changing amplitude, and this is the more rapidly changing quantity, the higher frequency. So what I can do is graph this amplitude in the following way. So this is x10 minus x10, and it's a cosine, so I can graph our cosine like this, and graph that envelope. I'm going to dot both of these. It's going to be a great picture. So this first one I drew, right, that's the behavior of this. I drew the second one because there's actually an envelope. Now the cosine omega t, this omega is much larger, and so we get this kind of an oscillation here. It came to a dead stop, increased, dead stop, and so forth. So that was the motion of the one pendulum. In this case, we're talking about the 2 masses, 3 springs. Okay. Now, if we look at the x2, the envelope function is going to be a sine. And let me just make sure I retain these points. So our sine would go to a maximum, back to a minimum, opposite, so forth, okay? And now we'll do this envelope again. Okay, yeah, and this function, this is the slowly changing part that I just drew, starts out as a sine omega t. So we're starting at rest when this one started full, and we're having this kind of a function. Okay, so this beat phenomenon is so common in nature, technology, elsewhere, that it's really good to have taken it through systematically. We started with coupled linear differential equations. When the coupling is weak, you'll get this stereotypical behavior here. Yeah, let's see how we're doing time-wise today. Good, we can say a little bit more about all this. But yeah, there's the beat phenomenon. There are good examples in music, by the way, when you have, say, 2 tuning forks with a similar frequency, you'll actually hear this beat phenomenon audibly. Piano tuners use this phenomenon to tune strings the way they want them. Okay, I'll send this up. Yeah, this would be this entire problem that we've done here would be a good one to take through really systematically and make sure you see every step I did. And I'm going to return to this normal modes discussion now. Okay. Yeah, I'm going to erase this. So yeah, I think this was pretty thorough. We'll find everything here. Just work it. See what happens there. Good. I'm going to bring the discussion back to those eigenvectors. I just wrote them down. You can say I just wrote this down formally. Let's bring this pendulum back into the mix. here's what I wrote down. So I said x1, x2, and we can think theta 1, theta 2 now, okay? It's analogous. Remember, that was part of your assignment, to prove the equivalence of these two Lagrangians. So x1, x2, I had an alpha 1, 1, 1, e to the I omega 1t, and I had an alpha 2, and these were just arbitrary constants with linear combination of these eigenvectors, minus 1 e to the I omega 2t. Okay. So this vector 1, 1 and this vector 1, minus 1, the vector 1, 1 is when they are in phase, okay? So x1, x2 are moving in phase, and so with the same frequency, so that's why they have, you know, each one is moving the same with the same frequency. So that's why we say 1, 1, okay, back and forth. Now the one that's 1, negative 1, that's when they're out of phase. So when this one moves forward, this one moves back, and vice versa. Okay. So that's this thing here. And these two types of motion are referred to as normal modes. So the normal modes are definitely clearly related, very directly related to the eigenvectors. So this was one kind of motion. What you can say is this total motion is a mix of this mode plus this mode here, a linear combination of those two modes. And like I said, we did it with x1 and x2, but in fact, if you just take the excursion along this ideal number line right here, which is my ruler, then you could even take these as x1, x2, even though they're theta 1, theta 2. Right? That really shows how they're equivalent. Good. So that's what these eigenvectors mean. So we're going to write next eigenvectors and what are called normal modes. This is one you're going to want to look up and learn about. That's what we're talking about now, normal modes, eigenvectors and normal modes. And I'm going to get a general relation. I think in this system it's so clear. The relation's so clear, you can directly visualize it. Same direction, opposite. What I want to do is write this thing down in the general case, the n degree of freedom case. So generally, we would have x1 all the way to x, so n of t would be equal to alpha 1, and then I'm going to have this matrix of eigenvectors. Well, before we get to the matrix, we're just going to have an eigenvector, so I'm going to have to call this A11, A21, A31, AN1. So the 1, the second index, says that that was my first eigenvector. It's written as a column, and there are going to be more of them. That's why I'm going to be talking about a matrix in a moment. E to the I omega 1t, and I go all the way out to the nth one, alpha n, A 1n, A n n, and this is the A sub n, e to the I omega nt. So that is the general version of what we did here. Okay. Really similar. the same. I'm gonna check the time because well, we'll do one more step on this. So the thing is, can this be written as a vector, matrix vector equation right here? So next, here's our vector x1, xn, and so columns of matrix A, ij are the eigenvectors. So the columns are the eigenvectors. And what we can do is, we've got a subscript 1 and a subscript 1 here, and alpha n, omega n. So we can actually write this as A11, A1n, AN1, ANN. We can, and this we can call alpha 1 e to the I omega 1t, alpha n e to the I omega nt. So what we have is a transformation. These are coordinates, but right, functions of time. These could also be referred to as coordinates. These could be our new coordinates. Coordinates q sub I. Or I could just call it a vector. New coordinates q. So this would be a transformation matrix from one set of coordinates, these are the original generalized coordinates, to another set of coordinates. That's where I'm going to leave this discussion. This is just a generalization of what we did explicitly. And of course, for your physical solution, you'd be taking real parts as well. Good, let's leave it right here. Do we have any other homework problems? Not yet. I think we have enough to do. Good, see you guys next time.